Next topic is amperometric transducers. Amperometric transducer is an example of electrochemical transducer. We already studied there are different types of electrochemical transducers on the basis of what parameter we are measuring or what type of electrical signal is obtained. When the electrical signal is obtained in terms of potential, that is known as potentiometric transducers. If it measures conductance, then that type of electrochemical transducer is known as conductometric transducers. Here in amperometric transducers, a fixed potential is applied to an electrochemical cell containing the analyte to carry out a redox reaction and the current is measured. Here we applied an external potential uh, based on the type of reactions to carry out a redox reaction, and the current obtained from after the redox reaction is measured. So the current is proportional to the analyte concentration. The current measured is directly proportional to the analyte concentration. When speaking to a sensor, one of the major important characteristic of a sensor is sensitivity. Here the sensitivity of amperometric sensors is greater than that of potentiometric sensors. We already studied the potentiometric sensors. Its sensitivity is limited to only the Nernstian response of the system under test. That is, a tenfold change in analyte concentration only increases the 59 divided by n millivolt. Okay. If tenfold change in analyte concentration occurs, then only a 59 divided by n millivolt change in potential only we can observe. For example, suppose n is 2, then 29 millivolt change for a tenfold change in the analyte concentration at a 25 degrees Celsius occurs. But in the case of amperometric devices, if the electron transfer is 1, then 20 times change in current density occurs. Change in current occurs if there is a tenfold change in concentration. In the case of amperometric sensors, suppose there is a tenfold change in concentration, then 20-fold change in 20 times change in the current measurement. Okay. So its sensitivity is very high compared to potentiometric sensors. Then moving to the amperometric cells. The cells which is used in amperometric transducers, that is the electrochemical cells used in amperometric transducers known as amperometric cells. Generally it consists of 3 electrode configurations. 2 electrode configuration also there, but generally for their practical purposes we are using 3 electrode configurations. So the cell consists of 3 electrodes. For 3 electrode configuration means it consists of 3 electrodes, one working electrode, then reference electrode and counter electrode. So it consists of a polarizable working electrode and a non-polarizable reference electrode. You know that what is working electrode? Working electrode is the where the electrochemical reaction occurs. Okay, this is the working electrode. So not where the electrolytic reaction occurs, electrolytic transfer occurs is called working electrode. It is polarizable in nature, and a non-polarizable reference electrode. Reference electrode is which is used for measuring the actual potential, right? So working electrode is polarizable in nature, and the reference electrode is non-polarizable in nature. This difference between the polarizable and non-polarizable is polarizable electrode means where there is a separation between electrode and electrolyte. Double layer is occur, the charge separation is occur. But in the case of non-polarizable electrode, that is in the reference electrode, there is no such a charge separation at the interface of electrode and electrolyte. So, for example, the working electrode example is platinum electrode. Then for non-polarizable electrode is silver chloride or calomel electrode can be used. Okay. Then the third type of electrode is counter electrode. Its area is much larger than the working electrode. Then a constant potential is applied using an instrument called a potentiostat. So this instrument allows when during the electrolytic reaction, the electrolytic current produced to flow between working and the counter electrodes, and there is no current flow through the reference electrode. So only current is flowing through working and the counter electrode. So therefore equilibrium at the reference electrode is not disturbed. Then again there is a current flow occur between working electrode and the counter electrode, right? But the counter electrode area is very large. I already mentioned that. Okay, area of counter electrode is very high, so its current density becomes very low, and hence only small deviations from the equilibrium state. So as the current does not any flow in the through the reference electrode, and also current density is very small for counter electrode, the measured current will only be due to the reaction of the analyte at the working electrode. So the produced current is directly proportional to the analyte concentration. Here the platinum and the carbon, glassy carbon, can be used as a typical counter electrode materials. Generally at the counter electrode, the reaction is oxygen evolution or hydrogen evolution reaction. Then moving to the working principle of an amperometric sensor. If a potential is applied to the working electrode wherein the analyte undergo oxidation or reduction on the basis of what type of potential is applied. Suppose the working electrode we apply cathodic potential, then the analyte undergoes reduction at the electrode. If here the OX indicate the oxidized form, then it undergo reduction by accepting that n number of electrons to produce reduced form of the analyte. Then according to the Faraday's law, reduction of 1 mole of electrolyte, that is here oxidized form, it involves the exchange of n of coulombs of electricity. So the cathodic current produced, current produced due to this cathodic reaction is proportional to the rate of electrochemical reaction VE by the following equation. That is, I is equal to NFAVE. Here I is the current, cathodic current, which is proportional to the rate of electrochemical reaction VE. Here I is the cathodic current, V is the rate of electrochemical reaction, N number of exchanged electrons, F Faraday, and A is the area of the electrode. But there is a problem that as the reaction proceeds, the oxidized form, concentration of that oxidized form at the electrode surface decreases, and soon a concentration gradient is set up near the electrode surface up to a certain distance from the electrode. That the distance between these two, near the electrode and up to a certain level, is called the diffusion layer. Okay, so the concentration of the analyte increases from the COI. Here it is called the COI, that concentration at the surface of the electrode, and the concentration gradient arises at the COI to COB. COB is the concentration of bulk solution. Okay, so the concentration of the analyte increases from COI to COB at the surface of the diffusion layer. COA is the concentration of that oxidant ion at the surface of the electrode, and COB is the concentration of the bulk of the analyte. So when the concentration of the solution is constantly, when the analyte solution is constantly stirred, then what happens? This concentration gradients become localized within a very thin layer. So the diffusion layer length is very low. Okay, so which is shown in the concentration profile of the analyte in the diffusion layer. So in the x-axis distance is given, and on the y-axis the concentration is given. Concentration at the electrode and also at the solution. Okay, at the electrode the concentration COI, and then it increases COB. Okay, concentration increases. When the distance increases, the concentration also increases. If it is stirred, then what happened? That dotted line indicates the stirred solution. Then what happened? The diffusion layer thickness is very low. If it is not stirred, then the curve, that line is in curve form, then it extended to further inside the solution. So this is what happened, or what is meant by the diffusion layer. So, for the reaction to proceed further, the analyte must be transported from the bulk to the electrode's surface. Bulk to the electrode surface across the diffusion layer. So, the rate of the reaction will depend on the rate of analyte mass transport. So, we need to transport this analyte from the bulk solution to the electrode surface, then only the current will produce continuously. Then only the reaction proceed further, then only the current produces more. This transport can occur by three types, three processes. One is diffusion. Diffusion means displacement of molecules or ions from a region of higher concentration to a region of a lower concentration. Then through the second process called migration of ions. This migration is due to the electric field. And the third process is called convection. Convection means the movement of the whole solution carrying the charged particles with it. The reproducible convection can be reproducible. It can be achieved by stirring the solution. That is, reproducible convection condition can be achieved by stirring the solution. So, three processes. One is diffusion, second one is migration, third one is convection. But for obtaining current proportional to the analyte concentration, the electrochemical reaction is carried out only under diffusion mass transport control by eliminating migration. So, only under diffusion, not by migration. So, we need to avoid migration process. This migration is suppressed by the addition of excess of an indifferent electrolyte to the sample solution. Then the supporting electrolyte ions will be the major current carrying ions. So, the externally added electrolyte, indifferent electrolyte is acting as a major current carrying ions. So, thus reducing the transport number of analyte ions. For example, potassium nitrate, sodium chloride or KCl can act as supporting electrolyte. So, in addition to the supporting electrolyte, it imparts good electrical conductivity to the solution and lessen the ohmic potential drop. So, this supporting electrolyte has two functions. One is acting as supporting electrolyte by acting as a major current carrying ions, and also it imparts good electrical conductivity to the solution and lessen the ohmic potential drop. Then when migration is prevented, now the current produced is only through the diffusion process. Then the rate of electrochemical reaction is equal to rate of diffusion of analyte from bulk to the electrode surface. And thereby the current produced indicates the concentration, or it is directly the current produced in the electrolytic cell or amperometric cell is directly proportional to the analyte concentration only. Okay. Next, we need to know that what is meant by limiting current and what is the relationship between limiting current and concentration of the electrolyte. So, before conducting the sensing experiment, that is the amperometric sensing, we need to fix the voltage to be applied. So, the potential to be applied for an amperometric measurements is determined from a voltammogram. So, what is meant by this voltammogram? When a voltage is applied to the cell and it is varied, then the current is measured. From the following experiment, the current voltage curve is obtained. This curve is called a voltammogram. So, this is a typical voltammogram where in x-axis the applied potential, we change applied potential and the current is measured against the varied applied potential. When the current potential increases, current levels off. Okay, so when potential increases at higher potential, the current becomes constant. That constant current is called the limiting current. At zero potential, the current flow is zero, and after it reaching the decomposition potential, its current increases. Okay, so when we apply a potential greater than the decomposition potential, the current flow starts. Okay, if it is cathodic potential, then it is positive, in the positive direction. Then suppose it is in the anodic, we apply anodic potential, then the current is in the form of negative. Okay, it comes to the negative side. So, here the case we applied the cathodic potential, right? So, it is positive, in the positive direction. And after increasing if further we increase the potential, then what happens? When it reaches a limiting potential, then the current is constant. That current is called a limiting current. Okay, this is called a limiting current. So that limiting current is proportional to the concentration of the analyte by equation which is given here. IL, which is limiting potential, is equal to NFA D divided by delta COX. And here IL is the limiting current, N is the number of electrons which is involved in electrochemical reaction, F is Faraday's constant, A is the surface area of the working electrode, D is called a diffusion coefficient of the electroactive species, here the oxidized form which undergo reduction. Delta is the diffusion layer thickness. Okay, then C is the concentration of the analyte. Here the term D by delta is indicated with the M0, that is the mass transfer coefficient of the oxidizing species to the working surface of the working electrode. Okay, to the surface of the working electrode. So D by delta is called a mass transfer coefficient. So what is meant by this E half value from voltammogram? Here in this figure, this voltammogram, there is a term called E half. E half is the potential at which half limiting current occurs. Okay, so E half is nothing but, in the voltammogram, the potential of the working electrode that corresponds to current that is exactly one half the limiting current is called E half. The potential which corresponds to half of the limiting current is called E half value. This value is not dependent on the analyte concentration, but is determined by the thermodynamics of the given redox reaction. So it do not depend on the analyte concentration. Hence, the E half value is characteristic of an electroactive species and helps in identifying electroactive species and also to distinguish one electroactive species from another in the same sample. Okay. If the E half values for various species differ significantly. So, using this E half value of different species, we can identify the or distinguish that species from one another, because it does not depend on the concentration. It is unique for different analyte species, different electroactive species. Okay, so you need to know what is meant by this E half value. E half is nothing but the potential at which the limiting current is exactly one half of the limiting current. Okay. Then in the amperometric measurements, under stable stirring condition, when we conduct the amperometric measurements at the stable stirring conditions at a fixed potentials which is greater than E half value. So we need to fix the potential which is greater than E half values, and the limiting current measured will be, at that condition the limiting current measured will be proportional to the concentration of the analyte. So limiting current is directly proportional to the concentration of the analyte when we fix the applied potential which is greater than E half potential, and the amperometric measurements are performed under stable stirring conditions. So this is also you need to know. Generally, if we analyze an amperometric sensor design mostly includes membranes with a selective permeability. So, diffusion membranes are included in designing the sensors. This is because the limiting diffusion current depends on the thickness of the diffusion layer. We already know that the diffusion current depends on the diffusion layer thickness, which in turn determined by the convection conditions. If we stir more, stirring rate increases, or stirring procedure if we conduct, the convection conditions it affect due to the convection process, it will be uniform. So the concentration change does not occur. So thereby a diffusion layer thickness is very small. Okay. So in order to obtain a reliable results in an amperometric determinations, if we perform it, we need to perform under stable and reproducible convection conditions. So we need to stir uniformly at a constant rate and a constant interval, etc. This is very difficult to be brought into the sensor design. Okay, so by performing this condition in a stable condition is very difficult to perform. Okay, so if the sensor is operating without convection conditions, so consider a condition in which the amperometric sensor working without convection conditions. So the diffusion current shows large fluctuations owing to the spontaneous convection in the solution that affects randomly the thickness of the diffusion layer. If we perform without convection conditions or without stirring, what happens? The diffusion current shows large fluctuations. So now the current only due to diffusion only. So the diffusion current shows large fluctuation due to the spontaneous convection. Okay, if now we are not stirring it, but there occurs some spontaneous convection in the solution that affects randomly the thickness of the diffusion layer. So by incorporating a membrane permeable to the analyte such that about only a 10 micrometer solution layer is sandwiched between them, the fluctuation we can eliminate here. So we can conduct the experiment without the convection or without stirring itself by using the membrane. So the membrane causes the current to be almost independent of the convection in the test solution. So this is the function of incorporating a membrane in the amperometric sensor. Okay, this is all about amperometric sensor. Next topic is biosensors. A biosensor is an analytical device which is used to determine the presence and concentration of a specific substance in a biological analyte. So this is also a sensor, but here the concentration, the presence and concentration of a specific substance in a biological analyte we need to analyze or we need to determine by the sensing process. A typical biosensor, its scheme is represented here. So it consists of a biological sample or biosample. Here the desired molecule we need to identify or the presence and concentration determined is the substance which is marked as X, which is the desired molecule. So a bioreceptor is present in biosensor. So this bioreceptor specifically identify or specifically absorb that particular desired molecule in the specific substance. So this bioreceptor this further identified by the transducer and then it processed into a signal. So it's shown in the display. A bioreceptor may be an antibody. Here, the bioreceptor may be a biological entity which may be an antibody, enzyme, nucleic acid or cell, whatever it is. Okay, then the transducer may include optical, electrochemical, maybe mass based or maybe temperature based and electric magnetic based transducers or transducer which can produce a change in or some molecule, biomolecule can change the if it change the optical property of a bioreceptor, then we can observe or we will get a, by using this transducer we will get a optical signal, maybe absorbance or transmittance, etc. Suppose it can change the property of a bioreceptor in electrochemical property, then we can use the some potentiometric sensor or amperometric method to analyze the bioreceptor. Then the amperometric glucose biosensor is a well-known example for biosensor. Okay, so amperometric method is the common method which is used in biosensing process, and we need to know the working mechanism of amperometric glucose biosensor. What is the function of this glucometer or glucose biosensor? Glucometers allow diabetic patients to monitor their blood glucose levels with a minimum amount of blood sample. So most of the glucose biosensors are based on amperometric transducers. So they utilize disposable electrochemical cells. So that glucometer consists of a disposable electrochemical cells called test strips. Okay, it consists of a test strips which is electrochemical cell. These strips consist of 3 electrodes. As in the case of amperometric sensors, it consists of 3 electrodes. One is working electrode, a reference electrode and the counter electrode. So a typical glucose biosensor, left side which is shown there and its components also shown in the figure. So there is a top support layer and then below that top support layer there is counter or reference electrode and fill detection electrodes also there. Then between this working electrode and counter reference electrode there is a spacer, a pressure sensitive adhesive, spacer made up of pressure sensitive adhesive. Then there is a bottom support layer, and in the working electrode layer, there is some yellow portion is there, shown in yellow portion, which consists of enzyme and mediator, okay, which is coated on working electrode. Then moving to the specification of that working electrode, where the oxidation or reduction occurs, the analyte undergo some redox reactions. It is a platinum strip. Generally, it is made up of platinum strip coated with a thin film of a conducting polymer like polyaniline. Then also contains enzyme glucose oxidase, is an enzyme used in glucose biosensor, and a mediator species, which all these are immobilized on the top of a working electrode. Second type of electrode is reference electrode, which is made up of silver chloride electrode. Then the potential of working electrode is controlled relative to the reference electrode. Then counter electrode, which is either made up of platinum or glassy carbon electrode. Then what is the working mechanism? If potential is applied across the working and reference electrode, and the current is passing between the working and the counter electrode is measured. So if we apply a potential between working and reference electrode, then what happens? There is electrolytic current is produced by the redox reactions of glucose with this glucose oxidase. Then the current is produced, which is passing between the working and the counter electrode, which is measured. Okay, so the current measured is equivalent to the quantity of glucose in the blood sample. So current resulting by the redox reactions of glucose, it is directly proportional, or it is equivalent to the quantity of the glucose in the blood sample, and is computed in terms of amount of glucose in milligram per liter and displayed in the screen. Okay, so this is the basic working mechanism or working principle of a glucose biosensor. So you need to know what is meant by glucose biosensor, and then what are the components in a typical glucose biosensor, then specification of 3 electrodes and the working mechanism. Then electrode transfer processes at the working electrode. When blood is placed on the test strip, glucose is oxidized to gluconolactone. Okay, glucose is oxidized to gluconate or gluconolactone by an enzyme called glucose oxidase. Okay, glucose oxidase. Then what happened? The step 1 is oxidation of glucose by enzyme. The enzyme GOX oxidizes glucose molecules in the blood to gluconate, and the cofactor of the GOX, that is FAD, glucose FAD, is reduced to FADH2. So generally every enzyme consists of a cofactor. Enzyme, there are different types of enzymes, are the simple enzyme, coenzyme, etc. Simple enzyme only consists of that enzyme part. Suppose if it is a coenzyme, then it consists of a cofactor. Here the glucose oxidase, it's an enzyme. It consists of a cofactor FAD, flavin adenine dinucleotide. So by the reaction with the glucose undergo oxidation, and the GOX FAD, glucose oxidase, along with that FAD undergo reduction. So glucose plus GOX FAD gives gluconate. This is the oxidized form of glucose, and GOX FAD undergo reduction to form GOX FADH2. Okay, FAD gets reduced to FADH2. Then in the second step, reoxidation of the enzyme by a mediator. So now the enzyme took the form GOX FADH2. So this GOX FADH2 is reoxidized to GOX FAD. So the enzyme gets reversed, right? We all know enzyme is a biological catalyst, right? So a catalyst maybe means what is the function of a catalyst? It remain in the solution. Okay, it does not undergo any conversion, so it gets reversed. So GOX FADH2 plus mediator. Here mediator do the function. Okay, it is reoxidized to GOX FAD by a mediator molecule, which is capable of existing in both oxidized and reduced forms and reacts quickly to donate or receive electrons. One of the example of mediator species is ferrocene derivatives. or quinone derivatives. These two can act as mediator. So GOX FAD H2 plus mediator gives GOX FAD. So the catalyst, we get the catalyst, biological catalyst back. That is enzyme. Which is came back plus reduced mediator. So the mediator in turn delivers the electrons to the working electrode. So the mediator get reduced form. So the extra electrons in the reduced form, it transferred to the working electrode for electrochemical measurements. So the movement of electrons occurs from the glucose to the working electrode. So first electrons in glucose, then glucose convert to glucose oxidase, then extra electron is transferred to glucose oxidase, then that electron is transferred to the mediator, then the mediator converts to reduced form of mediator, then the extra electron moving to the working electron. This is the process involves electron transferred in the reactions. So the role of mediator is facilitating the electron transfer, which is shown in the schematic representation. First, the glucose converted to glucon-lactone, and the electron is transferred to the mediator. Okay, mediator. Now the mediator takes the form of mediator reduced form. Okay, mediator reduced. Then the extra 2 electrons further moving to the electrode. So this is the whole process which is occurring in a biosensor.